This is lab 3 for Physics 2211, and this is the black hole lab. So the table of contents is what we're going to go through today. We have objectives, concepts, and we're going to find the mass of the black hole. We're going to simulate finding the mass, and then what does this mean? Then we're going to find the escape velocity, and then the orbit, which is the what if question. So the objectives of this lab to apply Newton's second law and Newton's universal law of gravitation, and we're going to use that to determine the mass of the black hole and the velocity needed to escape the gravity of the black hole and the planet. So that's some of the concepts that we're using. We have the position update formula, final position equals initial position plus average velocity times delta t. Then we have a velocity update formula, final velocity equals initial velocity plus net force over mass times delta t. The gravitational force formula, which is the negative gravitational constant, times mass 1 times mass 2 over r squared, and r squared is the distance between the two things that we're studying, and then the delta r, which is the r that will be squared, is r final minus r initial. So now we're going to find the mass of the black hole, and that's really just 3 steps. So we have to calculate the net force on the star by the black hole, use the position data to determine the star's position at each time step, and then we rearrange the universal law of gravitation to solve for the mass of the black hole. So m1, which is the mass of the black hole, is equal to the net force times r squared over the gravitational constant times m2, which is the mass of the planet. So essentially here we have all our formulas, and so this is the gravitational constant, 6.7 times e to the negative 11th. Then we have the mass of the star, which is 2e to the 30th, and then 86,400 seconds in 1 day, so that's the delta t is just equal to 1 day. Then we have our momentum formula, so p initial equals the mass of the star times velocity, so that's for p initial and p final. Then we have our delta formula, so we have the delta velocity is velocity final minus velocity initial. Delta p is p final minus p initial, obviously. Then we have dp dt, which is the change of momentum over time, which is the rate of change of momentum. And then we have net force here is actually equal to the rate of change of momentum. Then we have the F net parallel to where we took the net force and then we made it into the parallel vector of that net force. And then we did the same thing for the perpendicular force. So the perpendicular force and the net force are different, but this one for the perpendicular force, we actually made it so it was the net force total minus the net force parallel, and that equals the net force perpendicular, because if you add the perpendicular and the parallel forces, it equals the total net force. And then we had the code to calculate the mass of the black hole, which is the absolute value of the net force times r squared over g times m2. So here in the simulation, you're going to see that we actually had arrows determining each of the vectors of the net force separately. So the orange arrow, as you saw, was the net force, the pink arrow was perpendicular, and the blue arrow is parallel. And then we actually found the mass of the black hole, which is 1.67 times 10 to the positive 34. So it's just a lot bigger than the mass of the planet, as you can see. So what does this mean? So the rate of change of momentum, dp/dt, and the net force, F net, may seem the same, and they're actually coded the same in glow script, but they're actually calculated differently. So dp/dt is determined by the planet's velocity and the mass only. So you just take the derivative of the velocity and the mass, and you find dp/dt off of that. And then the net force needs the mass of the black hole to be determined, because the net force is equal to the gravitational force, which is negative g m1 m2 over r squared. So in conclusion, dp/dt can be determined using only the mass and the velocity of the planet, while the net force needs more information like the mass of the black hole and the distance between the planet and the black hole to be calculated. So finding the initial velocity for escape. So the initial velocity needs to be large enough to overcome the effects of the gravitational force of both the planet and the black hole. And because there's no net force pushing the ship away from the planet or the black hole, this initial velocity is the only thing going for it, and it needs to push it away from the planet and the black hole, so it needs to be high enough to do that. So right there on the left, you have the two initial velocities of the black hole, and then on the right-hand side, as you can see, we have the simulation of the ship leaving the gravitation of the planet and the black hole, both of them. So how do we find the initial velocity for escape? So we took the net force on the planet, which is the net force of the ship on the planet, plus the net force of the black hole on the planet. Then we had the net force on the ship, so that is the net force of the black hole on the ship and the planet on the ship. Then we took the velocity update, position update formulas for both the planet and the ship, and then we figured out after that. So essentially, the velocity needs to be high enough to on the ship to escape the F net of the black hole on the ship and the planet on the ship. So we had to have a high velocity to escape that, and then the planet would still be orbiting in a normal orbit as all that was happening. So what if we wanted the ship to orbit the black hole? So we'd have to have an initial velocity that's high enough to overcome the gravity of the planet, but not high enough to overcome the gravity of the black hole. So we actually had to lower the initial velocities a little bit, so then they would overcome the gravity of the planet, obviously, but not the black hole, so they'd shoot off into space like it did before.